So hello my dear students, I welcome you to NEET World. So today we will be continuing our discussion on electrochemistry. So particularly we will be discussing about Kohlrausch Law. So before going to Kohlrausch Law, we need to understand few more terms here. So let us discuss about these terms. Okay. So before going to the topic, I just want to announce about our new batch for NEET as well as JEE 2026 exams. Okay, so we are launching our NEET long term program from 1st July. Okay, so this batch is exclusively for long term students. Okay, and as well as we are also launching for JEE 2026 long term for both mains and advanced. So for more details, so you just contact to the whatever the number here you are seeing on the scroll. Okay, so now let us discuss about the topic. Yeah, so we have discussed in the last class the conductance, conductivity, resistance, resistivity, their relations and numericals on that, right? So today we will be discussing variation of conductivity and molar conductivity with concentration. See, in the last class we also discussed what are the factors affecting on the conductance, right? What are the factors we have seen? Solute-solute interactions, solvent effect. So more the solute-solute interactions, lower will be the conductivity. And the next solvent effect. Like solvent effect means size of a hydrated ion size we have considered. Okay, so larger the size, larger the hydrated ion size, lower is the conductance we have discussed. The next effect of concentration also there we discussed, but here we will be discussing more clearly. Then what I told you, so in that case, so conductivity means what? We will be indicating with the symbol K, kappa. So what is this conductivity?
G into G star.
So conductivity is like K, conductivity is given as the conducting power of all the ions present in one unit volume, right? So now upon dilution, it means upon dilution means what? Concentration will be decreased. So upon dilution, the number of ions present in unit volume decreases, therefore the conductivity value decreases. So what I am saying, if this is a total volume, okay, so we are talking about electrolytic solution present in this container. So this is a total volume. Okay, so now if I say unit volume out of it, so let us say this is a unit volume. So upon dilution what happens? The number of ions present in this unit volume decreases, therefore its conductivity decreases. So both conductivity, molar conductivity changes with change in concentration. Now conductivity always decreases with a decrease in concentration for both strong and weak electrolyte. So K value, so upon, you need to remember this, upon dilution conductivity decreases. So conductivity decreases, K decreases, and we have one more term, what is that? Molar conductivity or molar conductance increases. So this is increases. So why molar conductivity del M increases here? Because the for example, you know, Ostwald dilution principle. What is that Ostwald dilution principle? Alpha equals to root over Ka by C. For acid dissociation KVL writing, for base KBVL writing. Let us say Kc equilibrium constant, Kc by overall C. So equilibrium constant by C. So now alpha is inversely proportional to concentration. It means upon decrease in the concentration, degree of dissociation of electrolyte increases. It means if you dilute the solution, dilute that electrolytic solution, its degree of dissociation increases. Therefore number of ions increases. If number of ions increases, so more the number of ions, more is its conductivity. Therefore del M value increases. This Ostwald principle is applicable for weak electrolytes. Similarly, in the case of strong electrolytes also, del M value increases with increase in dilution, because the solute like particles between cation and anion, the volume increases means they will be move apart, na? So the force of attraction between them will be decreases. So as oppositely charged ions are far from each other, they are freely moves and conductivity value also increases. I mean molar conductivity value also increases. Clear? Okay. So you need to remember this because they may ask this based on statement based type of questions. Okay. Then next here we need to understand molar conductivity and limiting molar conductivity. See, molar conductivity means the conductivity value, that is del I am writing, okay, at some concentration, at some given concentration m. Okay, it means molar conductivity, we are using this symbol. When we are saying limiting molar conductivity, so this is the conductivity at zero concentration. What I am saying, del 0 means what? Zero concentration, or I am writing del infinite. Del infinite I am writing. It means conductivity of that electrolytic solution at infinite dilution. Infinite dilution means it is also zero concentration only. So volume is at infinite. So it means what you can understand from this? So much volume, like solution, like solvent is added. So the concentration will be tends to almost zero. So both are indicating same. So we can say this term as limiting molar conductivity or conductivity or conductance at infinite dilution. So both terms says same thing. Hope it is clear. So now here there is some C concentration. At C concentration I am saying del M. Okay, at zero concentration I am saying conductivity as del naught. Okay, so now for weak electrolyte, the degree of dissociation will be taken as see, now tell me, degree of dissociation increases now, it means conductivity also increases, right, for weak electrolytes. So del can be taken as, see, now tell me where we will be seeing maximum conductivity, at low concentration or at high concentration? Tell me, see, alpha value increases, degree of dissociation increases upon dilution. It means low concentration is nothing but dilution, no, more diluted. So more diluted, more number of ions, more is its alpha value. So maximum conductivity for a weak electrolyte is seen in which case?
Limiting molar.
Yes, this is the maximum. So now what I am taking is the ratio of limiting molar conductivity to the ratio of this thing, molar conductivity, will give us the value of alpha. So we are saying the alpha, degree of dissociation, is the ratio of molar conductivity at some concentration by limiting molar conductivity of that. That is what you need to understand. Okay. Now this you need to remember. We will discuss about this later. Next, just try to answer this. Which of the following is not correct? Molar conductance of solution increases with dilution. Is this correct or not? Molar conductance increases with dilution. Yes. Increases. This is correct. They are asking about not correct. Equivalent conductance increases with dilution. Yes, this is also increases. Okay. Specific conductance increases with dilution. Specific is different, na? That is K. So you need to consider the unit volume, not the total volume. So in unit volume, number of ions decreases. Therefore, K value, conductivity value decreases. So which is not correct here? Option 3 is not correct. So they are saying increases, but it should be decreases. So you need to tick this as your answer. Hope it is clear. So at infinite dilution, each ion, cation, anion plays a definite role towards the electrical conductance. Yes, this is correct only. I will tell you while studying about Kohlrausch Law. So option 3 is incorrect. Hope it is clear. Next. So now we will be studying about Kohlrausch Law and its application. So before going to study about this Kohlrausch Law, see, we have studied about molar conductivity, limiting molar conductivity. Now see, I want to draw the plots or graphs for molar conductivity, variation of molar conductivity del M with concentration. With what? Concentration C. Okay. So I want to draw plots for this. So while drawing this, let us first take for strong electrolytes. So how we'll get? So on y-axis I am taking molar conductance, on x-axis I am taking concentration. Okay, so now for strong electrolytes we have a relation like this: del m equals to del naught m minus a root c. Okay, so a is a constant here, root c is nothing but concentration. Del naught means what? Limiting molar conductivity. So we know limiting molar conductivity is the maximum conductivity that can be shown by the electrolyte. Okay, now since del m is nothing but this is the conductivity shown at this C concentration. So C can be 0 here, C can be some value here, some 0.1, 0.2, something like this. If it goes this side, it will be increases. Concentration increases on x-axis as we move this side. So this side conductivity, molar conductivity increases as we move upside. Hope it is clear. Now look here. So what we can say at at zero concentration. If C value is 0, what happens? This overall term will be 0 now. So del m equals to del m equals to del naught. Okay, so it means somewhere here if I wanted to put, so these both are equal at 0 concentration. Now what we know, as dilution takes place, the conductivity value increases. So it means as we move this side, see I am going from here to here, it means here maximum concentration. So I am going this side, means concentration is decreasing, right? We are tending towards 0. It means concentration is decreasing. So the graph looks like this for strong electrolytes. Okay, so now I want this at 0 concentration. 0 concentration means by extrapolating this graph, so I got a value of this conductivity at a 0 concentration. So this point, whatever the value here we get, so this value we can call del m naught. So what is this del naught? This is the limiting molar conductivity of this strong electrolyte. This graph is for strong electrolyte. Okay, so we can find limiting molar conductivity of strong electrolyte by just extrapolating the graph towards the y-axis. Right now, up to here it is clear. Now, how can we do it for weak electrolytes? This is our question. See, we can get limiting molar conductivity of strong electrolytes by just extrapolating the graph. But what in case of weak electrolytes? See, we know in case of weak electrolytes, alpha is inversely proportional to concentration. If alpha increases, degree of dissociation, if we want this as increases, so concentration should be decreased. Okay, so now upon dilution, degree of dissociation increases, means alpha value increases, so conductivity also increases. So conductivity directly proportional to alpha, can we understand like that? Yes. So from this point I am taking here molar conductance and here I am taking concentration root C. Okay, now tell me, so upon dilution concentration decreases, alpha value increases, del m also increases. They are something like oppositely, inversely proportional. No? So for inverse proportionality we will get something like this. No? Like this we will get. So if you observe this, so as concentration is getting decreased, see, so it is tending maximum, molar conductance going maximum for that electrolyte. It means upon dilution the conductivity value of weak electrolyte is tending to maximum. So it is observed that the molar conductivity of weak electrolytes upon dilution increases, keep on increasing, but it never touches the y-axis. It means we are not getting a constant value, it is keep on getting increasing. Molar conductivity of this weak electrolyte keep on increasing, it is never touching this y-axis. Have you observed this? Yeah. So from this what we can say, limiting molar conductivity of strong electrolytes can be calculated by extrapolating, but for weak electrolyte we cannot be calculated
because it is not constant.
Yes, it's keep on changing. Na? Yeah. So this is not a straight line, I mean it's just keep on increasing, just observe, understand it like this. It is keep on increasing like this. Okay, so see, if we are moving this side, its concentration is decreasing now. So concentration decreasing means alpha increasing now. So alpha increasing means conductivity value also increasing.
If we make concentration below, it will not touch the
Uh-huh.
axis.
Yeah, in that case also it is not undergoing complete dissociation, you can understand like that. Okay. So now one more thing you need to know is the limiting molar conductivity in strong electrolytes we have calculated just by extrapolating, but it is not possible in case of weak electrolyte. So the limit, so what is the point we need to highlight here? Del naught or del infinite of weak electrolytes cannot be calculated by
Graphical
extra
relating
flotation of
graph.
graph for weak electrolytes, but for strong electrolytes we can calculate. It means we need some method to calculate this limiting molar conductivity of weak electrolytes. Okay, so for calculating of limiting molar conductivity of weak electrolytes, we have an indirect method. We have which method? An indirect method that is given by Kohlrausch. So who is that? Kohlrausch given an indirect method to calculate the limiting molar conductivity in case of weak electrolytes. So how can we calculate this? Let us see this Kohlrausch law. Okay, so now we need to understand what exactly Kohlrausch law. So Kohlrausch law says that at infinite dilution, what he is saying, at infinite dilution, see for example here I am using HCl. It is a strong electrolyte now. So whenever I am taking this electrolyte in the aqueous medium, what happens? It will releases H plus Cl minus ion. Look at here, and I am taking now acetic acid also. This is a weak electrolyte. So what are the ions it will generate? Even it is weak electrolyte, it will generate
O minus H plus O.
H plus,
CH3CO minus.
like this we will get. Okay, now listen here, at infinite dilution an ionic species, whether cation or anion, contributes a fixed value at a given temperature towards total conductance of electrolyte, irrespective of other ionic species in combination with it. So it means, try to understand it clearly. So whatever these cations are coming from, whatever the species, whatever this H plus ion originating from, whether it can be from HCl, from acetic acid, from sulfuric acid or any other species, always the ionic conductance of H plus ion will be fixed. It means H plus ion, whenever it is present in the electrolytic solution, its conductivity value will be fixed at
Same goes for Cl minus.
at what? Infinite dilution. So that value is around the ionic limiting molar conductivity of this H plus ion will be around 350. I will show you the value. Okay, 350. So for all the H plus ions, irrespective of source it is coming from, what is the ionic conductivity contribution for H plus ion? 350. Like that, for every ion there will be fixed contribution towards a conductivity value. Like that, for H plus ion we have like this. Similarly for OH minus ion also
Same.
like that. So it's the value is not always 250. It varies from ion to ion. 350. So for example, limiting molar conductivity of OH minus ion we will be taking it as around 200. Okay, these are experimentally found values. Okay, they will mention the values. No need to worry about that. Okay, so now in other words, what we can say, the same definition understand from contribution of any ion is constant at infinite dilution at a given temperature. At particular temperature, the contribution of any ion will be having a fixed value. It means different ions have different values, but one type of ions, for particular ion like H plus ion will be have a fixed value of 350. 349.6, let us make it 350 for our understanding or for remembering purpose. OH minus having around 199, let us understand it as a 200 value. Okay, like this. So now I will be showing you this table. See, H plus ion is having 349.6, Na plus ion having 50, K plus like this, like this, like this we have. These are the cations. Here you can see anions are also having respect to ionic conductivity values. Now from this you should observe one thing. The ion which is having maximum conductivity value is which one? From cations. So H plus will be having max ionic conductivity, limiting molar conductivity. Max limiting molar conductivity is for which one? H plus from all cations. From all anions, OH minus. So OH minus ion is the anion which is having max ionic conductance, limiting molar conductance at infinite dilution. You can understand, like these are the 2 points you should remember. Okay, so remember this as 350, this as 200. Okay, now let us understand the remaining topic also here. So what are the applications here we have? For example, I have shown you this one now. See, we know for acetic acid it is a weak electrolyte. I want to calculate the limiting molar conductivity of this weak electrolyte. COOH, I want to do this. So how can we do this? It's a strong electrolyte or weak electrolyte? So we cannot find it directly because we cannot draw take from the diagram, I mean graphical method. So for this we definitely want to use this Kohlrausch Law method. So for calculating the limiting molar conductivity of acetic acid, we need to take those strong electrolytes which produces these ions. Which ions? Ions that are present in this weak electrolyte. What are the ions present? One is acetate ion and other one is these two ions we require now. So these two ions, what are the strong electrolytes giving these two ions at infinite dilution? So for example, I can say H plus ion can comes from HCl, which is a strong electrolyte. So I am giving limiting molar conductivity of HCl as X. Why? Because HCl is a strong electrolyte, so it will be having a limiting molar conductivity. We can get the value of this by extrapolating in the curve. Yes or no? Because it is a strong electrolyte. Now I can also give limiting molar conductivity of sodium acetate. So tell me, sodium acetate weak electrolyte or strong electrolyte? So tell me, this is weak electrolyte or strong electrolyte? Strong electrolyte. So let us take its value as Y. Okay. Now this XY value, they mention some other values. For our understanding, I am taking XY like that. Okay. Now take one more thing here. See, for this I want acetate ion and H plus ions only. I do not want this chloride ion and I do not want this sodium. So we need to remove that now. So we should take limiting molar conductivity of NaCl. That is what? Extra part. That means we need to remove that. Take it as Z. Okay. So now tell me, what are the things contributing these ions from there? Limiting molar conductivity of take it as HCl, because they haven't given for H, they given for HCl. So you take it like that. Okay. Place again H plus we got. We need this
sodium acetate.
Limiting molar conductivity of sodium acetate.
But we don't need.
We do not require chloride ion. We do not require sodium ion. Minus del infinity of NaCl. That's it. So add the required parts, remove the unnecessary unrequired parts. That's it. Okay. So what we'll get for HCl, the value is given as x plus y minus z. So this is your answer, that's it. So they may give some numericals here, put that values and get the answer, that's it. Clear now? Yeah. So let's move further. Is this clear? Now what I told you, del naught HCl, so ionic conductivity of H plus and Cl minus, and del naught H2SO4 I am writing here. So if it is molar conductance, how many H plus ions it is giving? 2. So 2 H plus ions you should write, plus sulfate ion. So these values will be what I told you, the ionic conductivity values will be fixed at particular temperature. What is that value? Around 350.6. So let us take it as 350 like this. Okay, and even if I write HNO3 also, H plus plus
NO3
minus. So these values are fixed irrespective of source, at a particular temperature. Okay, hope it is clear. Up to this one also clear, no? Yeah, let us discuss few more things. This is also done. So what we have calculated, what are the application we have seen? Calculating the limiting molar conductivity of any electrolyte from an individual ionic conductance. From individual ionic conductance we can calculate now. Individual ionic conductance comes from indirect method, like taking the strong electrolytes.
plus y minus.
Yeah, like that. Next, just try to solve this question. The molar conductivity of NaCl, HCl and sodium acetate infinite dilutions are given here. See, just now I have taken x, y, z now. They mentioned x, y, z values here. Put the values and give me the answer. This is NEET 2021 question. Just based on our discussion only. So I just want answer for this. Do it, man.
1.
Maybe just put that values and you will get. Okay, next question here we have. So tell me, for these 3 acids, 3 ions, 3 electrolytes, they have given the values and they are asking the limiting molar conduct same like above. See, this is the acid they have mentioned. We need to calculate limiting molar conductivity of this acid, value of limiting molar conductivity of this acid. So how can we write? Limiting molar conductivity of this acid equals to limiting molar conductivity of this anion is coming from here. So that is how much? Directly we will do that. 224 because anion is coming from here plus and we need H plus. It means it is coming from here 203 and minus 38.2. So it will be how much? 7 2 4 minus 38.2. So how much we will get? 338 point. That's it. That is the only option we can have, right? Any other question here we have? No. So what is the other application I have told you? Second application is finding degree of dissociation of weak electrolyte. See, for example, acetic acid, if we say this is a weak electrolyte, gives sodium acetate H plus. So now let us say at time t0, at initially at the beginning, C concentration I am taking, this will be no ions at the beginning. So at some time t, when this acid dissociated to some extent, what happens? Some of this acid is converting into its ions, means its concentration decreases. So that decreases now. So C minus something. So C minus something means it is dissociating now. So we can give the dissociation with alpha. What is its concentration? C. So C minus C alpha we can write. So this is the amount converting into this form now, and also this one. Okay, so from this, what is the equilibrium constant we can get? Ka equals to concentration of products by reactants. So acetate ion concentration H plus ion by like this. So what is the concentration it has? C alpha, that is also C alpha. So can I write C alpha whole square? By C minus C alpha. So I am writing C into 1 minus alpha. Is there any issue? Just write this here, you will get C like that. Okay. Next, from this Ka will be equals to how much? C square alpha square means I am writing alpha square. So C square by C into 1 minus alpha we have now. So I am removing this. So what we are remaining with? C alpha square by 1 minus alpha. If degree of dissociation is very less for this weak electrolyte, what happens to alpha value? Very less, na? So that is almost negligible when we compare with the 1. So therefore it will be becomes what? Alpha square if degree of dissociation is very less. For the weak electrolytes only. This is applicable only for weak electrolytes, not applicable for strong. Okay, this is what Ostwald's dilution principle. Okay, so now Ka will be equals to what? C alpha square. Okay, from this what I can add? Alpha will be equals to Ka by C root. That's it. So alpha is inversely proportional to C. Lower concentration, greater dissociation for weak electrolyte. Right? So now we got it like this now. This is the what? Ostwald dilution principle. From that we only got the remaining discussion also. And the next here, from this if I want to calculate Ka, so I have told at the beginning, I have told you how can you calculate alpha using limiting molar conductivity. So it is a ratio of del m to del m naught. So it means wherever you have C like alpha value, there you have to substitute. That's it. So if you substitute here, you will get a relation like this: C into del m by del naught m square by 1 minus del m by del naught m, like this. Okay. So you can simplify, you will get a relation. So from this they may also ask you to draw a plot also, or what is the slope also they may ask. Like this, from there they can also generate a question. So if you simplify, you can get a equation. Okay, hope it is also clear. And any other doubts you have in this? No doubts? Okay. So then next, so we can wind up this session, and if you have any doubts, we will discuss personally. So thank you for watching. If you have any queries, feel free to ask me in the comment box. Thank you.